Okay, this is problem set 1, number 3. And we're trying to prove if A and B are independent, given that the probability of A given B plus the probability of A bar given B bar is equal to 1. So A and B are independent if the probability of AB is equal to the probability of A times the probability of B. So we use properties of conditional probability and expand the following two terms to the probability of AB over the probability of B plus the probability of A bar times B bar divided by the probability of B bar is equal to 1. So using De Morgan's law, we can then expand the second term further to equal the probability of A plus B bar over the probability of B bar is equal to 1. And then again further, we can expand this term to be equal to 1 minus the probability of A plus B, just using axiom of probability. So in the fourth line, we know that the probability of A plus B is equal to the probability A plus the probability of B minus the probability of the intersection AB. So since it's a minus, we come to the conclusion that we have 1 minus the probability A minus the probability of B minus a minus resulting in a plus, so plus the probability of AB all over the probability of B bar is equal to 1. So the probability of AB over the probability of B, this has all just been copied all down because we haven't used it. So now we can take the last part of the second part of line 4, and so it's the probability of AB divided by the probability of B bar. We can take that out and put it here, and we're left with 1 minus the probability A minus the probability of B all over the probability of B bar is equal to 1. So we can factor out 1 over the probability of B plus 1 over the probability of B bar. So we have that first part. And then the second part, since we have 1 minus the probability of B, that equals the probability of B bar. So we have the probability of B bar minus the probability A all over the probability of B bar. So now we want to combine these two fractions to form one fraction on line 7. So when we combine these two fractions, we end up with the probability of B plus the probability of B bar all over the probability of B times the probability of B bar. But the probability of B plus the probability of B bar is equal to 1, so this goes away. So we end up with just the probability of AB divided by the probability of B times the probability of B bar. So back up here in line 6, we have the probability of B bar minus the probability of A all over the probability of B bar. The first part of this fraction just ends up being the probability of B bar divided by the probability of B bar, that results in 1. And then we're left with negative probability of A divided by the probability of B bar. The ones cancel out, and then we can move the probability of A divided by the probability of B bar to the other side. So we have the probability of AB divided by the probability of B times the probability of B bar is equal to the probability of A divided by the probability of B bar. The probability of B bars can cancel out, and we would come to the conclusion that the probability of AB is equal to the probability of A times the probability of B, and therefore A and B are independent.